Assalamualaikum warahmatullahi wabarakatuh. Uh, so today we will be doing the 2023 October-November variant 23 P2 Java. So let's start. Define acceleration. So where is this? Basically, acceleration it's a full levels definition, rate of change of velocity. If you do not remember the definition, you can just uh, take it out from the formula of the acceleration, which is acceleration is equal to change in velocity over time. Basically, if there's anything divided by time, uh, with a change like acceleration if you can say velocity, formula velocity is change in displacement over time. So when something is being divided by time, it's called the rate of change. Like in maths, we do dy over dt. If you take it, rate of change of y, just give me a second. All together. The rate of change of velocity. Okay. Small aircraft is flying horizontally at a speed of 42 meters per second at a height of 63 meters above horizontal ground, as shown. The aircraft drops a small parcel. The parcel is released from the aircraft at the instant shown in figure 1.1. Where resistance is equal to 0. Let's call this time is equal to 0. On figure 1.1, draw a line to show the path of the parcel as it falls from the aircraft to the ground. Okay, so let's say that hypothetically the parcel is attached to the aircraft like this, steering it. So in this instant, it has um, it has a vertical velocity 42, but it doesn't have any horizontal sorry, it has a horizontal velocity of 42, but no vertical velocity. So if you drop this from the aircraft, from let's say these are cut off this instant. So the acceleration which is acting on this parcel is basically the acceleration due to gravity. So its vertical velocity will increase, but its horizontal velocity it will remain constant. So basically its direction will look something like this. So just vertical velocity is increasing. And if you like imagine aircraft dropping fast, this is what you would imagine. It will not directly go like this. It won't happen because there is a vertical component of velocity, which is also to be considered. And you have to also make sure that the gradient, which is this, it is increasingly more negative since it's accelerating. So velocity is also increasing. Calculate the time taken from the instant of release to the instant the parcel reaches the ground. So over here, you know that the parcel is dropped from a height of 63 meters, and over here its velocity is 0, and it doubles 63, and so we can use the equation of motion as is equal to ut plus half at square. Since we have the initial velocity, which is 40, so it is 0, displacement which is 63, and acceleration which is negative, sorry, it is positive 9.81 because it's in the same direction. So we can use this equation. 63 is equal to 0 t plus half 9.81 t square. So 9.81 t square is equal to 63 into 2. Square is equal to 126 over 9.81. So t is equal to under root 12.8440. So t is equal to 3 point 3.58 seconds. Now, you see the majority of the values in question are two significant figures, so that's what we will choose. That's what is usually significant figures which is used. 3.6 meters per second. Yes, Anara. Okay. Um, Calculate the vertical component of the velocity of the parcel immediately before it reaches the ground. So basically, it's asking us to find the vertical velocity when the particle hits the ground.
Assalamu alaikum.
وعليكم السلام ورحمة الله وبركاته. كيف الحال؟ Acha. So, uh, to we have the initial velocity, we have the final velocity, and we have the we need to find the final velocity, and uh, we have the acceleration. So we can use the equation 2as is equal to v square minus u square. Acceleration v square is equal to 2as plus u square. V is equal to, let's put in values, 2 9.81 63 plus 0 square under root v is equal to 35.1. Take this to a significant figure 35 milliseconds. Determine the speed at which the parcel reaches the ground. Okay, this is a good question. So basically, uh, we have the horizontal component of velocity. Speed is basically velocity without the direction. So we can calculate the resulting velocity. Horizontal velocity, which is 42 millisecond. Resulting velocity, which is 35 millimeters per second. So the speed of the speed is basically keep resultant velocity of the two velocities 42 square square is equal to 42 square plus 35 square. V is equal to under root 42 square plus 35 square, and we get 54.671, approximately 54.55 seconds. The principle of conservation of momentum. Principle, this is also a definition which you have to memorize. Total momentum in a in an isolated system remains constant. Okay, so this is the first question. It tells you what the whole question is going to be about. So if they ask the definition of momentum, so it's basically going to be momentum. A ball X has mass 240 grams and moves in a straight line or a horizontal frictionless surface with an initial speed of 16 meters per second. Ball collides with a stationary ball Y that has mass 480 grams. After the collision, ball X is stationary as shown in figure 2.1. Show that the speed v of the ball Y after the collision is 8 seconds. So we just need to use the equation of momentum. Initial momentum of particle 1 plus initial momentum of particle 2 equal to basically initial momentum is equal to final momentum. M1 V1 plus M2 V2. Mass of the initial particle is 240. We don't need to convert it to kg because it's an equation, so it will give us the same answer. Into initial velocity 16 plus ball y 480 mass, initial velocity is 0 since it's at rest. Stationary ball hence 0 velocity equal to final velocity. Ball x is stationary 240, when final velocity is 0 plus final velocity of y 480 v is 0, so v is equal to 240 into 16 divided by 480. 41 is 480 divided by 40 is 2 there. 8 it's the second final velocity. Calculate the total kinetic energy of the ball to the collision. So change in kinetic energy for any change, if it's either kinetic energy, gravitational tension energy, is final kinetic energy minus initial kinetic energy change. We're talking about change. So it's final minus initial always. Final kinetic energy is 480. No, I think over here we will need to use the SI units, so 0.48 kg into it's half mv square, right? Half m velocity is a square minus initial half 0.24. Mv is 16 square Calculate. Basically, you get negative 15 joules. There's a change of 15 joules. They're asking for the change, so you don't need to write the sign. That's right, 15. Acha. The collision in B lasts for a time of 2 milliseconds. So let's say this is the intermediate. They are in contact for 2 seconds. Assume that the contact force between the balls is constant during this time. Okay. Determine the magnitude and direction of the force exerted on ball X by ball Y during the collision. So they're asking us to find the force, and we have mass, and we have velocity, and we have the time. So the only equation which we can use is resultant force is equal to change momentum over time. So basically, we need to find the change in momentum of x. The momentum of X is equal to the final momentum, which is 0, minus initial momentum, which is 0.24, mass into velocity, 16. Which we get negative 2.4 into 16 minus 3.84. This is the change in momentum. And we have the time, which is 2 seconds. So, oh, it says 2 milliseconds. Sorry. Two into 10 power, negative 3 seconds. So, F is equal to negative 3.84 divided by 2 into 10 power negative 3. This is 1920. Okay, so they said determine the magnitude. So in the magnitude, we just need to write the value. We do not need to write the direction. So it's 1900 Newton to SF, and direction is to left because it's traveling over here and it collides over here and then it stops. So basically, this force must be over here because it accelerated in this direction. Since it was moving over there and then it came to a stop. To the left. Compare the magnitude and direction of the force exerted on ball Y by ball X during the collision with the answers. For the magnitude and direction of the force. Since the momentum is conserved, so the same momentum must have been transferred to Y. So the resultant force remains the same. So magnitude is equal magnitude, but since it moves in the opposite direction, so it will be in the opposite direction. Basically, this is Newton's third law. Okay. State the principle of moments. Now we know the next question is about moments. So moments is basically uh, for a system P in equilibrium. يعني it, it, it is balanced like it is a seesaw and they are moving.
Assalamu alaikum, bro.
وعليكم السلام ورحمة الله عليكم كيف الحال؟ الحمد لله. To be in equilibrium, uh, the sum of clockwise moments is equal to the sum of anti-clockwise moments. A rigid uniform beam rests on a pivot at its center as shown.
ये कौन सा पास पेपर है?
ब्रो ये ओ यार मैंने गलत चैट पे भेज दिया सॉरी दिस इज विंटर 23 20 अक्टूबर नवंबर 2024 वेरिएंट 23.
ठीक है.
Okay. Rigid uniform beam rests on a pivot at its center as shown. Load pivot container such to a load of weight 2.6 Newton is suspended from the beam at distance from the pivot. A wooden cylinder of weight 4 Newton is suspended from the beam at a distance of 0.4 meter from the pivot on the opposite side of the pivot to the load. The cylinder rests in a container of water. The lower part of the cylinder is immersed in the water to that age. Uh, yeah. Wooden cylinder of weight 4 Newton is suspended from the beam at a distance of 0.4 meter from the pivot on the opposite side to the pivot to the load. From this load to the opposite side. The cylinder rests in a container of water. The lower part of the cylinder is immersed in the water to depth h. Initially, h is equal to 0.1 meter. Initially, and x is equal to 0.4 meter. 4. The system is in equilibrium. Use the principle of moments to show that the upthrust Q exerted by the water on the cylinder is 1.4. Let's use the principle of moments. Clockwise moments, we have um, this force over here into this distance perpendicular 4 into 0.4 equal to now sum of anti-clockwise. First anti-clockwise we have load of 2.6 newtons. 2.6 into 0.4, which the question told us is x 0.4 plus upthrust is acting over here. So technically, in respect to the pivot, it is also acting in the anti-clockwise direction. So we can say u into 0.4 because it's this perpendicular distance. From here, we calculate u. U is equal to 0.6 minus 0.04 by 0.4 is 1.4 Newton. Yeah, because basically we use the system of moments conservation. Density of the water is 1 into 10 power 3 kilograms per meter cube. Calculate the area of the circular cross section of the cylinder. So we know that upthrust is equal to density into gravity into volume. We have the upthrust, which is 1.4. We have the density 1 Newton power 3. We have gravity to 9.81. And so we need the volume. And volume is, let's first calculate volume. Volume we get 0.000142 cube. And now we know that the cross-sectional area into height is the uh, volume. H we have, they gave us H we have, this is 0.1 meter. So area is 0.000142 divided by 0.1. So area is equal to 1.4 into 10 power negative 3 meters square. Simplify. More water is gradually added to the container in B so that depth H in figure 3.1 gradually increases. Let's suppose the water is now this level. So H becomes this. The length X is continuously adjusted so that the system remains in equilibrium. On figure 3.2, sketch the variation of X with H. Use the space below for any word. Okay, so this is a very fun question, Hamza. So if we see that upthrust is equal to rho g v, if we use the formula of volume, rho g area into H, rho g is equal to upthrust. So you know density is constant, gravity is constant, area is constant. So we can say that upthrust is directly proportional to the H. And so if H increases, so the upthrust also increases. Now over here in the momentum question, you know that let's just look at this formula. So if upthrust is increasing, that means that, and we only, they're talking about X, right? And we only have in the clockwise moment this force of this spring cylinder. So um if the upthrust increases, this needs to remain same. So that means that this X will decrease, X which is 0.4, this will decrease. Now, how will this increase? We know that H is increasing linearly, but the uh, volume also increases um, linearly. So X will decrease linearly. So you know that when H is 0.1, X was 0.4, and in negative line from over here, So we need to see if, let's suppose, when x becomes 0, what will be, let's say when x is over here, it's so small because h has become too large. What will be the value of h? So we can see that 4 into 0.4 is equal to, this becomes 0. This cancels out, plus u. U is basically rho gv, rho g a h into 0.4. We'll just put those values here at the same time. 4 into 0.4, 1.6 divided by 1 into 10 power 3 to 9.81 to the area we calculated, 0.4 into 10 power 3 to 0. So when x is 0, h is 0.81 into 1.4, 10 power 3, 10 power negative 3 cancels out. H is 0.29. 1 to, but we take to the significant figure. So 1 point over there, 1 point over 2, 5, 2, 6, 2, 7, 2, 8, 2, 9. We draw a straight line. Define, question for define stress is going to be around elasticity. Stress is basically force over per unit cross sectional area. We can just use the formula stress is equal to F over A. Find the definition. Strain. Strain is extension over original length. So we say extension per unit unstretched, which is the original length. Two wires X and Y with equal unstretched lengths of 0.84 meter are suspended from fixed points that are at the same horizontal level. Lower ends of the wires are attached to a beam. Negligible mass. The beam is horizontal and in equilibrium, as shown in figure 4.1. Wire X is made from a metal that has a Young modulus of 1.9, 10.9 pascals. Wire Y is made from a different metal, which means it has a different Young modulus. A load of weight 80 Newton is suspended from the beam at a point that is equidistant from the two wires. This load causes both wires to extend by 0.47 millimeter. Determine the cross-sectional area of wire X. Okay, so we know when wires are attached parallelly, the, the weight is distributed. So, and since it's at equidistant, that's what will get 9 Newton. This will get 9. Now they ask the cross-sectional area of wire X. So we know that Young modulus is equal to formula force into unstretched length over cross-sectional area over extension. So A is equal to FL over Young modulus into extension. A is equal to force 9. Unstretched length is 0.84 meter. Young modulus is 1.9 into 10 power 9. To unstrap into the extension, it is 0.47 millimeter to 10 power negative. So we get cross-sectional area 8.5 into 10 power negative 6 meters cube. Wire Y has a greater diameter than wire X. Explain without calculation whether the Young modulus of the metal from which wire Y is made is less than, same, or greater than 1.9, i.e. X. From here you can see that it has a greater diameter, it has a greater cross-sectional area. So in these question, like this question, we did similarly this question where we had to find the variation of X with H. We just like use the formula of the question, which is Young modulus is equal to FL over AE. So I know you see which are constants. Force is constant, length is constant, extension is constant. So you know that we can say that Y is inversely proportional to cross-sectional area. And what is cross-sectional area? It is diameter over 2 square pi r square. So if the diameter is increasing, if diameter increases, that means that cross-sectional area also increases. And if cross-sectional area increases, that means the Young modulus decreases. So we say that it is less than 0.9 and 0.9 since F, L, and E are same, and so A is greater. Basically, you need to explain what we just did right over here. Put those into words. That's the last job. Waves. A stationary wave is formed on a string XY that has a length of 0.48 meter. Figure 5.1 shows the string at one instant in time. Speed of the wave on the string is 1400 meters second. On figure 5.1, draw a cross at one position that is a node, another cross at one position that is an antinode. Label the node N and the antinode K. In stationary waves, you know that nodes are those points which do not move. So if you can imagine this wave a few seconds later, it will look something like this. So which points are not moving? These points are not moving. So we can say node. And with the points of maximum amplitude, those are antinodes. Antinode. And we only have to label one because they said one. We label two, we won't get the mark. So that the wavelength of the wave produced is 0.32 meter. Okay, so So is basically wavelength of a stationary wave is basically one whole frequency, which like a normal wave. So sorry. So this is one stationary wave. So how many stationary waves are these? This is one, this is two, but this is, let's say, so this gives us one wavelength, right? This is one wavelength. So how much is this part? Like this part over here, it will give us half wavelength. This part. So how many parts of these are this wave? One, two, three. So can we write that three parts, which is wavelength over two, is equal to 0.5848 meter, is the total length of the string. From over here, we can say that 0.48 into 2 over 3, which is equal to 0.3 meter. Calculate the frequency of the wave. Easy. Know that V is equal to F lambda from O level. Speed we have 1400 and lambda 0.32. Frequency we get is 4400 hertz. A source of sound waves of frequency 780 hertz is on a rotating platform. Okay, this is the source of sound. Speed of the source is 39 milliseconds. Sound is detected by an observer that is large distance from the rotating platform as shown. Speed of sound in air is 20. Sorry. Speed of sound in air is 320 milliseconds. Calculate the maximum frequency of the sound detected by the observer. So frequency observed is equal to frequency of source 780 to speed of sound. Maximum frequency will be when the uh, source of sound is moving towards the object. So we will do minus speed of sound minus speed of source. 39. We get 890. At time t equals to 0, observer detects the sound emitted by the source when it was in the position shown. On figure 5.3, sketch the variation with t of the frequency f of the sound detected by the observer for one complete rotation of the platform. Calculations are not required. Okay, so initial position it is equal to 0. So let's say this is stationary over here. So when it starts moving, it moves away from the observer. So its frequency will decrease. Let's say this is initial frequency, 780. This calculation is not required, so we will not calculate. So it decreases linearly since P2 plus. Speed is same, but its frequency will decrease. This is initial frequency. Equal to this. Large distance. Variation time to the frequency of the sound emitted by the observer for one complete rotation of the platform. So over here is 39, but it's 39 in this direction. So the time it takes to move from over here to here, from and from over here to here, speed it's actually increased. So 39, this is at 39, it's something it's in the vertical. 39 will be over here exactly. So if its speed is gradually increasing, then if it's moving away, then the observed frequency will gradually decrease. So the frequency over here decreases to the initial position is this, and then it increases. Then to the initial position. Find resistance. Resistance V is equal to IR, voltage over current. So scientific difference per unit current. A cylindrical metal wire of length 2.4 meter in cross-sectional area 10 power negative 6 meters square has a resistance of 0.33 ohms. There is a current in the wire of 4.7 amps. Determine the resistivity of the metal from which the wire is made. We know that resistance is equal to resistivity into length over cross-sectional area, rho L over A. So resistivity is equal to resistance, which is 0.33 ohms, to cross-sectional area, which is 8 to 10 power negative 6 meters square. You can try the unit divided by length, which is 2.4. We get 1.1 into 10 power negative 6 ohm per meter. Calculate the charge that passes through the wire in a time of 5 minutes. Know that current is equal to charge over time. Charge is equal to current, which is 4.7 amps, into 5 into 60, because it's 5 minutes, and we convert it into seconds. So, which is 1400 volts. The electrons, charge carriers in the wire have an average shift velocity 0.16 millimeter per second. Given the number density of charges in the metal, we will use the equation I is equal to nave, which is current, charge density, area, shift velocity, is the elementary charge, which is given in the formulas in the beginning. Elementary charge. We need to find the charge density. So N is equal to I over AVE, equal to current is 4.7. Area is 10 to 10 power negative 6. Shift velocity is 0.16 into 10 power negative 3, and 6 is millimeter, into elementary charge is 1.6 into 10 power negative 90 meters. Now we just calculated elementary charge is 0.3 into 10 power 28 meters per meter. That many electrons in meter cube of the wire. The wire in B may be considered to be a fixed resistor. It is connected in series with a thermistor to a battery that has negligible internal resistance. This circuit symbols to complete. Figure 6.1 to further circuit diagram first. Fixed resistor connecting series with a thermistor. So symbol of fixed resistor is a blank empty box, and for thermistor is empty box but with this symbol. Out of the resistor. We can do it like this. Fixed resistor series with a thermistor. Explain without calculation how the power dissipated in the wire, just do right here, changes as the temperature of the thermistor is increased. Okay, good question. So we know that power is equal to voltage into current. Just use equations, makes life easy. And current in the whole circuit, so if we the temperature is increased, then the resistance decreases. They are inversely proportional. Temperature. The graph looks like this. Inverse proportional graph. Temperature. So if its resistance is in decreasing, that means that the total resistance of uh, the circuit decreases of the so the current increases since V is equal to IR and voltage is constant. The resistance decreases, current increases. Over here, voltage is constant since it's a battery. So current increases, the power also increases. Power increases as resistance of the resistor decreases. So current increases. That's the answer. Where do you want to complete table 7.1 to show the charges in terms of the elementary charge E on each of the flavors of pot. This is easy. This is very simple to remember. You just remember cut. These are all of these, which is cut is charm up top, and all of these have plus 2/3 elementary charge, and all of the others except cut they have a negative 1/3. You can also remember by like the nature of the name, like up is positive, top is positive, down is positive, down is slightly negative. Strange is also not a very positive word. They will have a negative elementary charge. So for okay, so fork and anti-fork chart. So fork has +2/3, anti-fork has -2/3. Change the sign is -1/3, +1/3, -1/3, +1/3. State the name of the class group of fundamental particles which baryons and mesons belong. Baryons. Basically, it's tough to memorize. Compare baryons and mesons in terms of their constituent particles. Basically, baryons, i.e. proton. You don't need to write this, I'm just writing for explanation. And neutrons made up of 3 quarks. Both of 1 quark and 1 antiquark. This stuff is basically memorization. You just need to ratify this. Describe beta positive decay in terms of the fundamental particles. So we know that positron is released when a proton converts into a neutron. That's when a positron and a neutrino is released. So a proton is composed of up, down, and neutron is composed of up, down, down. So an up changes to a down force. That's basically what you need to write. And a positron and neutrino are emitted.